Okay, we're going to continue on here. Dare I say it for the last time, chapter 14 here. And last time we talked about two different type of titration curves. We talked about weak acid and strong base. And again, we have a similar looking titration curve. Got a little bit still of that S-type thing. Here, we will probably start a little bit higher on the initial pH than we did in the strong acid, as it's a weaker acid, depending on the concentration, obviously. A couple other points. We still have those 4 important points along the way. And that is before you start titration, after you start titration, but before the equivalence point, and at the equivalence point, and then after the equivalence point are the 4 parts. Remember, it's a little bit different than strong acid, strong base titration. Here at the very beginning, we do have pretty much a Ka type of problem because we have just a weak acid that's present. Again, does require 1 ice table. You could do it in molarity because you haven't added any volume or anything at that point. You could solve for X, and X would be your H plus concentration, and then you could go into the pH equation. As we start adding some base to our acid in this titration, we will approach kind of the second part of the titration curve, which is before the equivalence point. Now, before the equivalence point, it will require 1 ice table at least. That does need to be done in moles because you are adding volume. So again, the molarity will continue to change. Really, the purpose of that is you should, as we talked about, pretty much always hit a buffer at that point in this type of titration. And that is the purpose really of the first ice table, is to figure out really the concentration of your buffer that you're going to make. So after that first ice table in moles, you can convert it back to molarities in the total volume. And at that point, you do, again, as we talked about, have 2 options. You could do a second ice table to figure out the pH, a sort of common ion buffer type ice table. Or you can just go right into the Henderson-Hasselbalch equations, which again might be the easier move since it is a buffer at that point to get the pH. That will bring us to our third point, which is the equivalence point. And at the equivalence point, that's when the moles of the acid equals the moles of base. And what we will have left really at this point in titration is just a salt. And that salt came from, or part of that salt came from a weak acid, which means its conjugate base will go through hydrolysis and react with water. And it will react as a base, which means it will accept a H plus from water. And you will need really 2 ice tables, one to figure out the concentration of the salt is the first ice table, which does need to be done in moles because you're adding volume. Once you're done with that first ice table, back to molarity with the total volume, then you have a traditional sort of hydrolysis type problem that you would do next, which would require a second ice table for the reaction with water. Because it's going to produce hydroxide, we would expect this type of titration to be basic when we reach the equivalence point. Again, different than the strong acid, strong base, which would be more neutral at the equivalence point. Then clearly here, past the equivalence point, we're just dropping more base in there. So you would need an ice table. And the purpose of that ice table is to figure out how much strong base that you basically dropped in there. You will still have that salt that will go through hydrolysis, as we talked about. But in comparison of the salt being a base and the sodium hydroxide, for example, as a strong base, the strong base is a much stronger base than the salt, and it will be the major contributor of OH minus, for example, in that solution. So we ignore the salt's contribution and we look at the strong base. That means that basically that first ice table will get you the concentration of the strong base, which will allow you to get the OH minus concentration and then get the POH, and then you could get to the pH. Any question on any of those parts there? The last type of titration we talked about there was sort of an opposite titration. Here we have a strong acid and weak base. In this one, remember that we're actually adding acid to the base. So we're actually starting with the base. And that's why when we look at our terribly sketched here titration curve, and not too bad, it is upside down. We're starting with a high pH because we have the base that we're starting with basically in the beaker. And as you add the acid, the pH should come down. We still have pretty much the same 4 points here. We have our before we start, before the equivalence point, at the equivalence point, and then after the equivalence point, basically. And it is pretty identical-ish to this guy, except that we're going downwards. The difference here is instead of a weak acid we're starting with, we're going to be starting with a weak base at the beginning before we add anything. So that's going to be more of a KB type of ice table problem, which you could do in molarity because you haven't added anything. As you approach that second spot there, as you start adding some acid to this before the equivalence point, you once again will hit a buffer at this point. So you'll need one ice table to figure out the concentration of your buffer. This will, most of that run, maybe not all the way to the equivalence point, but most of that run as you get towards the equivalence point will result most likely in a basic type of buffer that's going to happen. And so you could need one ice table to get that concentration. Once again, probably the Henderson-Hasselbalch is the move there, and that'll get you to your pH. Here at the equivalence point, we once again will have just a salt that's left over. And because this salt basically comes from a weak base, it will be a relatively strong conjugate acid and will go react with water and go through hydrolysis. It will act as an acid and donate the H plus to water, and that will produce H3O plus. And we would expect at the equivalence point, because of that, that we're looking more of an acidic equivalence point in this type of titration because of that hydrolysis that's happening. So much like the other one we just talked about there, pretty much a double ice table on this move here. First ice table is for the concentration of the salt. Second one, again, is a hydrolysis type of ice table that you could do in molarity after you convert it back to molarity after you're done with the first ice table. Lastly, here on the fourth step, as you go past the equivalence point, in this case, because we're adding the HCl, we're just adding a lot of extra acid in there, and we're building up the H plus concentration, which is why we see a pretty significant drop there, right, in the pH after the equivalence point. Requires one ice table. Purpose of the ice table is to figure out the concentration of the strong acid you keep dumping in there. And because that's a strong acid, and even though the salt is still present, the strong acid is going to be stronger than the salt and the major contributor of H plus in that solution. So you would take the concentration of strong acid and basically figure out the pH from that, because that would equal the H plus concentration. So really, these two titrations are pretty much identical in the sense of the calculations that you need to do. You either have a Ka or Kb to start with. You got a buffer before the equivalence point. You got a hydrolysis problem at the equivalence point, and you have either a strong acid or strong base type problem as you go past the equivalence point. And again, as I talked about earlier, kind of knowing where you're at, especially with these two types of titrations, can really help you focus in on the calculation before you do it. Because again, if you're before the equivalence point, you know you should end up at a buffer type calculation. If you're at the equivalence point, you should be doing like a hydrolysis calculation. So just knowing that before you kind of jump into the calculation can help you sort of focus on how to maybe do it correctly. Any questions on any of that there? All right, then let's do one last example here, which clearly you finished at home. And we're going to check your answers here as we go through it. All right, so we have 4 different spots here on this titration that we're doing. We have nitrous acid, and we're adding some sodium hydroxide. So here, our nitrous acid is down on the bottom, and the burette is going to be our sodium hydroxide. So again, we're adding our sodium hydroxide to our acid. By the way, we do know that this obviously is a weak acid, as we have a Ka value given to us, and that's a strong base. So this is basically a titration of a weak acid with a strong base. That's kind of the first one we just talked about there a second ago. All right, so we got part A, the initial constant pH when we had 80 milliliters at the equivalence point, and then after we had 105 milliliters, we basically want the pH. As I mentioned last time, when you have problems like this, you could assume that each of these sort of points, if you will, are starting from 0. Like you open it up and you go 80, then you stop it, and then you open it up from 0 and go to the equivalence point, and you open it up and go directly to 105. So we don't sort of continuously add the volumes or anything like that. I just kind of keep them separate. All right, so clearly the initial solution is before my titration starts, and before my titration starts, I have just the weak acid in there, and I got a Ka of 4.5 times 10 to the minus 4, and I'm doing 0.1 molar. Minus 4 and 0.1 molar nitrous acid. So again, at this point initially at A, that is pretty much all I got floating around in that solution is this weak acid. So again, it is a weak acid problem here to figure out the pH. So we're just going to do it like we've done before. We're going to take our weak acid, we're going to break it apart into H plus and NO2 minus. We're going to initially use our concentration here, which we can because, frankly, we haven't added anything yet. So that is the molarity. So that's all good. We're going to go zeros. We're going to go minus X plus X plus X. That means at equilibrium, we got 0.1 minus X, X, and X. Any questions on the table there? Like normal, we're going to go into our Ka expression here, which is in this case the concentration of H plus times the concentration of NO2 minus divided by HNO2, and obviously that equals our 4.5 times 10 to the minus 4. Popping those numbers in is going to give us basically x squared divided by 0.1 minus x equals 4.5 times 10 to the minus 4. We could assume that x is equal to 0. And if you did that, of course you did yesterday, you know that that's a bad assumption because you're at like 6.7%. So you do need to go back and actually solve it a different way, which in this case would be the quadratic. So we're going to multiply this to the other side. That's going to give me x squared is equal to 0.000045 minus 4, we got there 0.5 times 10 to the minus 4, and that should be an x, I believe. Okay, now we're going to combine everybody. So we're going to bring everybody back here to the other side. X squared plus 4.5 times 10 to the minus 4, x minus 0.000045 equals 0. That's going to be our A, B, and C here as we go into our quadratic. So popping in some of those numbers, that's going to give us x is equal to minus B plus or minus the square root of B squared. So that's 4.5 to the minus 4 squared. Minus 4 times A, which is 1, times C, which is negative 0.000045. That means here inside the square root, 0.00001802. Now we're going to square root it there. And we'll go with a, how about a 0.0134. That's all going to be divided by 2 times A, which in this case is 1. So that's going to be divided by 2. That again is going to give us our traditional 2x's here. So minus 4.5 to the minus 4. We'll do the plus first, plus 0.0134 divided by 2. Going to give us an x value of 0.006475. We do the minus, which clearly is not going to be a good one. Minus 0.0134 divided by 2, going to give us a negative 0.006925. Obviously, here we're looking for the pH, which is X. So negative is not going to work so well for us in this case. Any questions on that there? All right, so that obviously is going to equal our H plus concentration, which would be 0.006475 molar, as that equals X basically. That could go into our pH minus the log 0.006475, going to give us a pH here of We'll open up with a rousing 2.19 pH, which is acidic, so that's good since we're starting with an acid, right? So you got a basic pH here, that would not be so good. Any questions on that? Also a good reminder, make sure you check your assumption as it may not always be correct. Yeah. Although I think you might get a fairly close number if you did the assumption, just blew by the checking part, yeah. But it would still be incorrect, yeah. Any questions on that part? All right, so now we're going to actually start the titration here. So we're going to do B, and in B, we're going to drop 80 milliliters of it, and we're starting with 100 milliliters of the nitrous acid. So in B, we still have our Ka of 4.5 times 10 to the minus 4. We're starting with 100 milliliters of 0.1 molar nitrous acid. And we went on to know the pH after we drop in there 80 milliliters of 0.1 molar sodium hydroxide. So obviously here we're going to get a reaction between our acid and base, and we're going to take our acid and we're going to react it there with our base, our sodium hydroxide. And a little double displacement reaction, a little sodium nitrite, and a little bit of H2O there. Now, because we're starting titration, I know a couple of things really right off the bat, right? I know I need to do this table in moles because we're adding volume. I also know in a second where I am in the titration. So let's see where I'm at. We're starting with this guy. We are adding this guy. So we need to get the moles of each of these. So again, that's like 0.1 liters times 0.1 moles per liter for our acid. That's going to get us here 0.01 moles. We'll do a similar calculation, except that it's 80 milliliters of our base, so 0.08 times 0.1, gonna give us 0.008 moles, and 0 on this guy. Am I before, after, or at the equivalence point? I am definitely before, because I looked at the problem and the next step is at the equivalence point, so I'm probably before it. But I know that for sure because what I'm adding is less moles than what I started with, which means I am before the equivalence point. That also means that now that I know I'm before the equivalence point, I should definitely end up with what type of problem? I should end up with a buffer problem because it's a weak acid and strong base. Let's see if that's true. We're going to do the change here, which is our sodium hydroxide, 0.0080, 0.0080, and a plus 0.0080. That's going to get us here at equilibrium 0.01 minus 0.008, 0.002 moles. 0 of this guy, and 0.008 moles of this guy. Our total volume at this point, we started with 100, we added 80. That's a total volume of 180 milliliters. So again, we're going to convert these guys back to molarity just to be on the safe side. That way we're always in most likely the right unit that we want, which is molarity. So we're going to take our 0.002 divided by 0.18. 0.0111 looks good. 0.008 divided by, oops, come here, 0.180. 0.0444. Again, if you weren't sure where you're at and not sure what type of problem you have, you again can still look at the ice table, and you have this guy here and this guy here left over. And once again, you hopefully at this point should be able to recognize that these guys are related to each other. That is a weak acid, basically in the salt of its conjugate base. So as we correctly predicted, we ended up in a buffer at this point. And that means that we could go into the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the base over the acid. pKa is equal to minus the log of the Ka minus log 4.5 times 10 to the minus 4. Looks like a 335 on the pH there, our pKa value. So putting that in there, 335 for our pKa, the log, once again, we want to make sure we get our base on top, which is this guy. So we're going to go 0.0444 divided by 0.0111 and do a little dividing here. A little logging and a pH of 3.95. Yeah. Questions on that one there? So if we take a look at sort of where we are at here, right? You know, we have pH. We started at like 2.19. We've now kind of raised the pH here to, I missed it, but we raised the pH there down to 3 and change. So we are progressing up the titration curve, obviously, at this point. We're now going to come to part C, which is the equivalence point. Fix that. And now we should, again, kind of see that rise in pH definitely to the equivalence point as we had a buffer, and we're going to basically blow through the buffer here. And that's, again, why we're going to see that jump in pH. So we're at the equivalence point here, obviously starting still with our same stuff. We got 100 milliliters of 0.1 molar nitrous acid. And we're going to add it to 0.00 molar sodium hydroxide, and we're at the equivalence point. Again, here, they did not give you the volume to reach the equivalence point, which you will eventually need so that you know the total volume here. Again, there are a few ways to figure it out, but let's start with what we do know, which is I have HNO2, and I still have my sodium hydroxide reacting, giving me my sodium nitrite and my water here. And once again here, we want to do this in moles. So we definitely know we have 0.1 times 0.1 gives us 0.01 moles. Now, to get the moles of this guy, I do know I'm at the equivalence point, which means the number should be the same. Yeah. Which now that I really know the moles that I should have, and I have the molarity of the sodium hydroxide, molarity is moles per liter. I know the moles, I know the molarity. The liters would be moles divided by the molarity is one way you could figure it out. So you would take your 0.01 and divide it by 0.1, and that's going to give you approximately 0.1 liters, which is 100 milliliters is basically what you need to get to the equivalence point. You also could have done a little M1V1 equals M2V2 action, as this is a 1-to-1 relationship, and you could have did 0.1 molar 100 milliliters equals 0.1 molar and my V2. Dividing this to the other side, my 0.1 molars are going to cancel, and you'll be left with 100 milliliters as well. So you could have done that as well to figure out the volume. Or lastly, if you have a 1-to-1 relationship and they actually have the exact same concentration, you'll need the exact same volume to reach the equivalence point. So that's a third way if they happen to be the same concentration. Any questions on how you can get to the equivalence point volume? All right, so now that we have our moles and our volume, we can continue on here. We're going to have 0. Good news at this point is you hopefully should not pick wrong, since there's only one number to pick from, and that is minus 0.0100, minus 0.0100, and a plus 0.0100. That is going to give us, as we expect at the equivalence point, nothing happening on the left-hand side, as that's pretty much the definition of equivalence point. They equal each other. We will end up here 0.0100 moles. Now, this is the part where, again, you need to figure out that volume, because our total volume here is not 100 milliliters, but it's 100 plus 100. And that's a total of 200 milliliters at this point. So we do need to divide here by 0.2 liters And again, that is the importance of being able to figure out the volume here. So we'll take 0.01 divided by 0.2 is going to get us 0.05 molar. Any questions on that there? All right, so again, you really should know at this point, because you're at the equivalence point, what should be happening. And if you don't, you can still use your ice table, and pretty much the only thing you got left there is, as we talked about before, what you should expect, a salt. And this salt should go through hydrolysis because, again, it came from a weak acid. And because it came from a weak acid, this salt will be a conjugate base. And that is how it's going to react with water, which happens to be right there. Those two are going to start reacting, basically. It is not the sodium part of that, right? It is the NO2 minus part that actually is reacting. The sodium, again, is a neutral salt, so it's not going to do anything. So even if you could not figure out what NO2 is, or NO2 minus is it an acid or a base, logic should tell you that it doesn't have a hydrogen to give, so the only thing it could do is accept the hydrogen, which is what we would expect it to do because, again, it's a base, so it should accept the H+. So again, we're going to get that H+ actually transferred over this way. It will make where it came from always, and it is going to produce hydroxide. So also, as we know, we should expect our pH here now to be basic, right? Because we are producing hydroxide. So the equilibrium concentration from the first table, which is really the whole purpose of the first table, is to get that concentration now becomes your initial concentration here on this table. And we do want to do it in molarity, which again is why it's important to convert this back into molarity here after the first ice table. This is going to be zeros and our normal x's, so minus x plus x plus x. This is going to be 0.05 minus x, x, and x. It's going to go into our K expression here, which is our products over our reactants. This is what type of K, by the way? This is a K B. And it's a KB that you need because, again, you're producing hydroxide. So remember that if you have hydroxide on the product side, KB action, H3O plus on the product side, or H plus, Ka type of problem. So we don't have the KB given to us, so we do need to convert the Ka into the KB to do this problem. So I'm going to squeeze it right there. I think our KB is going to be our Kw, which is 1 times 10 to the minus 14, divided by our Ka, 4.5 times 10 to the minus 4. And that's going to give us the proper value that we want to use. A very common mistake people will roll with the Ka value here. 2.2 times 10 to the minus 11 is going to equal x squared divided by 0.05 minus x. Here I'm going to do my assumptions, so I think I'll roll that on the next page here. So we got 2.2 times 10 to the minus 11 equals x squared, basically 0.0, was it 0, I think, right? Yeah, 0.05 minus x. So here we're going to assume x is equal to 0. So that's going to give us basically x squared over 0.05, 2.2 times 10 to the minus 11. We're going to multiply and then square root action it. So we'll go 0.05 and now square root it. Going to give us too many zeros to count in this early morning, but x is equal to 1.054 times 10 to the minus 6. We do want to check it, so we're going to divide it by 0.05 times it by 100. And I think we actually should be okay in this particular case. We're not even 0.1%. So the check here is good, yes, in this case. So that x, if we go back to our ice table here, again, does not equal the H plus concentration, but equals the OH minus concentration. So that x is going to be the OH minus concentration. We'll throw an M on it. That means we could calculate the pOH here, minus the log of 1.054 times 10 to the minus 6. And that's going to get us there 1.054 to the minus 6. And we'll call it 5.98. So again, at this point, if you got confused, what sometimes happens, people think that's the H plus concentration, and you calculate this pH, which is really the pOH, and you think it's 5.98, it really should not make sense to you based on the type of titration it is, because at the equivalence point, you know it should be basic. So again, if you got confused a little bit along the way and thought this was the H plus concentration, and you thought that was the pH, it should not make sense. So let's get a number that does make sense, which is the pH is 14 minus my pOH. That's going to be a 14 minus 5.98. Finally here, we're going to go with an 8.02 pH at this point, at the equivalence point, which is definitely basic and what we would expect it to be. Question on that there. Yeah. I got it from the first ice table. It's the moles and then dividing by the total volume at that point. So we started with 100. We added another 100 of the base to get to the equivalence point. So that's 200 milliliters total volume. Other questions? And obviously that right here, which is the sodium nitrite, is the source basically of the nitrite that's coming through and reacting with water at this point. Yeah. Other questions? All right, so obviously we are rising up there on our titration curve there to our equivalence point. We are now ready to rise up again and switch over that way. It's a bad turn there, I think, more like a right angle turn there on my titration curve. All right, so number D there, or letter D, we're at 105 milliliters added. So let's see where we're going to end up here. So D, still our same Ka, 4.5 times 10 to the minus 4, still starting with 100 milliliters of our 0.1 molar nitrous acid. And it was 105, right? I think, yeah, 105. And we're going to add 105 milliliters of our 0.1 molar sodium hydroxide. So again, we're going to get our reaction here. So we can do our ice table. And that is what we're adding. That's what we're starting with in this case. And we're going to get our sodium nitrite and our water. Once again, need moles since we're adding here. So we're going to start with the same starting moles that we had there of 0.01 moles. For our sodium hydroxide, we're going to go 0.105 times 0.1. Going to give us 0.0105 moles and 0. Again, we know hopefully that we are after the equivalence point here because the moles of what we're adding is greater than the moles of what we started with. So again, at the equivalence point, we were equal. Now we have added more moles of what we're adding, which is the base. So we are past the equivalence point. Remember that there's now a switch that occurs. This guy is actually going to be the limiting reagent. And the change is actually going to be the acid here at this point. And that means, as we would expect, we reached the equivalence point and used up all the acid and continued on our journey here. We're going to have none of that left. In terms of our base, we will have this left. And we'll have some of this guy here left. At this point, our total volume, we have 100 milliliters, 105. That's a 205 milliliters as our total volume. We're going to convert back to molarity here. Obviously, also converting that into liters. So divide by 1,000 or move the decimal point. Going to give us here for this guy 0.002439 molar. And 0.01 divided by 0.205. I lost the 5 there. Wait, put it in there. And going to give us 0.04878 molar. So again, at this point, we do have a couple of things left over. We got this guy and we got this guy. Are they related to each other? Is this a buffer? This is not a buffer, right? So just because you got two numbers doesn't make it a buffer, even though you might want it to be. We have what we should expect happening past the equivalence point here, which is we have that salt that's a base, and we have this guy, which is a strong base. And as we talked about, we're not going to be concerned at this point with our salt because, again, all the strong base has to do is go in for a swim and it's going to break apart and produce hydroxide really quickly. So it's going to be the major contributor to the OH minus or pH really at this point. And if you just think logically about it when you do a titration, if you're just adding base, right, past the equivalence point, you're pretty much just loading up your beaker with a bunch of hydroxide because you just keep dropping it in basically. So that is going to be actually our hydroxide concentration. Once again, not our H plus concentration. Going to allow us to get to the pOH of minus the log of 0.002439. Going to hit us a 2.61 pOH, which in turn will get us a pH of about 1139. Question on that one there. So again, we can see if we look at sort of our little bad sketch here, we were at 8-ish over here on pH. We then jumped up to 11-ish, I think we just hit. So we're definitely up there, way past the equivalence point at this point now. Any questions on any of those calculations there? So clearly for the three types of titration curves we talked about, or titrations we talked about, you should have the ability to calculate the pH anywhere I choose along that titration curve. Or if I'm really mad at you, like 400 points on that titration curve, that would just be the exam one titration curve, 400 points. Give me the pH all the way through. I'm kidding, by the way. Don't drop now. All right. Any questions on how to do any of these calculations? So again, the key is, as I mentioned before, really is understanding where you are in the titration curve, understanding what type of problem you should be doing. It makes the calculation way easier than just sort of jumping in and putting numbers together and trying to figure it out. You could still figure it out pretty easily, even if you don't think about it. Once you get to the end of your ice table and see what's left over, you very quickly could sort of hopefully figure out really what you should be doing at that point based on what's left over. Any questions on any of that there? All right, the last thing we're going to talk about in chapter 14. Did I say last and 14 in the same sentence? I think I might have. So we're going to talk a little officially here about acid-base indicators, even though we sort of touched upon it as we've been going through the chapter. But acid-base indicators, as we talked about, are really, for the most part, similar to like a weak acid. So what I mean by that is IN here means indicator. There is a protonated form of the indicator, which has the hydrogen on, kind of like a weak acid. And there's like a deprotonated form where it kind of releases this hydrogen, also like a weak acid. So depending on the ratio of either the protonated form, the guy still has the H plus, and the one that does not have the H plus, as to which color you will see. And that is because for the most part, as we talked about, indicators work over a pH range. And they usually will change colors as you kind of go from one end of the range to the other. And that's really why they're useful, because you definitely want to choose an indicator where you will actually see a color change occur near your equivalence point, because that's typically why you use an indicator. It is a visual reference, right, to tell you, hey, you should maybe stop your titration because you're probably at the equivalence point, right? So it's kind of like the stoplight, if you will, that you should lay up your titration. Now, if you choose one where you don't actually see a color change occur near the equivalence point, it's frankly going to be useless for you because it's just going to stay the same color and you won't know really where to stop, right? And then when it finally does change color, it might be too late, right, for you to stop. Or if you pick an indicator that changes color way too early in terms of the pH, it will change color way too early and you won't have any more reference of where you should stop. So ideally, as you can see here, these are all different pH indicators, acid-base indicators, and you can see they work over a wide variety of ranges. Here's something like crystal violet is working over like a pH range of like 0 to just under 2, and you get this color change, and actually changes to a few colors. As you can see there, it goes from like yellow to a greenish to a bluish, right? So for example, if you chose that as your indicator and you're doing a titration where the pH is going to be basic, you're just going to be blue all the way to the end there, right? And you'll never know really where you should stop because the color change occurred way too soon for you, basically, in that case, right? Now, if you were doing a titration and say your pH was like 8, again, at the equivalence point, and you choose like this guy, this Alcazar in yellow, it goes from yellow to red, but it works over a pH range of 10 to 12, and your equivalence point is way back at 8. So you're going to be yellow, right, all the way through there, and you're not going to see an actual color change where you need. So you need to kind of dial it in. This is why a lot of times we all choose our favorite one ever, right, which is phenolphthalein. And that works over, as we talked about, from that 8.3 to 10-ish range. And that is colorless at 8.3 to kind of a pink color as you get closer to 10. That is why they choose that indicator, for example, like the titration you did in Chem 50, which was probably acetic acid, some vinegar perhaps, and acetic acid has an equivalence point in the pH of 8 point something. So that's why they also scream at you that you want the lightest color of pink, like you could barely see it, because that will put you ideally near that 8 point something number, which technically is colorless here on your indicator. But as we talked about, even if you miss it by a drop, it will turn it pink. So if you get the lightest shade of pink at a half a drop, something like that, that should put you pretty well near your equivalence point. And the difference between it turning to slightly pink and colorless, because again, it goes vertical, as we talked about, right? As you get to the equivalence point, it's not going to be a very big difference in the volume. So your calculation will still be really, really good in terms of that. So when you're choosing an indicator, you definitely want one where you can definitely see that color change occur early on. Now, if you're doing a titration, for example, of a diprotic acid, how many equivalence points would you have? How many hydrogens does a diprotic acid have? 2, which means if you're doing like a diprotic acid, your titration curve will look something like this, where you have 2 equivalence point 1 and equivalence point 2, one for each of the hydrogens that come off, right? Technically speaking, if you had a triprotic acid, you would have 3, but good luck trying to get that third one to come out. It probably won't, because as we talked about when we did the calculation, not a lot of H plus is coming off right at the very end there. So most of it's coming off at the front. So you probably will still see something like this, but technically speaking, it would have kind of 3 sort of equivalence points, one for each of the hydrogens to come off. That's different than a monoprotic acid, like a lot of examples we've been doing, where you see just 1 equivalence point basically that's happening for the 1 hydrogen that's basically coming off and reacting. So, you know, you'll see these different types of equivalence points. So if you're doing like a diprotic acid, maybe the first equivalence point is acidic, but maybe the second one is basic. So depending on which one you might want to stop at, you might want to choose one versus the other indicator. Although I have seen people choose 2 indicators in the same titration, one for the first one and one for the second. But usually, as you know, if you already change color on the first one, by the time the second one changes, it's not going to be the color you think it's going to be, right? It's going to be a mixture of it all. So it kind of becomes a blur of color and stuff like that. Any questions on that there? All right. So for this titration here, a little nitrous acid, a little potassium hydroxide. From our list here, which ones would be good indicators to use, perhaps? Take a look. So first off, just take a look at the little table here. Again, these are some different acid-base indicators. And as I mentioned, they have usually a specific color and sort of when they're acidic range, if you will. And as they get closer to that basic range, that's sort of the color they kind of change. And that's based on sort of that ratio of either the protonated indicator to the deprotonated indicator. This is the pH range that they sort of work off of here. So again, when you're going to choose what indicator you might want to use here, you really want to think about, obviously, what type of titration you're performing. So this happens to be the one we just did, pretty much. That is HNO2, which is a weak acid. And we have KOH, which is a strong base. So that's pretty much like that example we just did the calculations for. And if you take a peek at that one that we did, the pH was around 8-ish, yes? And that is what we would expect in this case. We would expect that the equivalence point would be basic. And it would be basic because at the equivalence point, we would have a salt that came from a weak acid. And because that salt came from a weak acid at that equivalence point, it is going to act as a conjugate base when it reacts with water and goes through hydrolysis. It's going to accept the H plus and it's going to produce hydroxide, which means it should be basic at this point. And that means that when we go through our list here, I'm going to say this one is going to turn way too early for us, as we definitely are probably again in that 8-ish range. Definitely too much, too soon, too soon, too soon, too soon. Now, this one does go to 7.6, but again, if you did your calculation, you're probably going to see it in the 8-ish range, which means technically speaking, that's going to probably be a little too soon for you as well. Here, and by the way, at 7.6, it probably has already changed color at that point, which means you're not going to get that visual change that's going to occur. This guy, Creosol red, is a option, right? That at least takes you into the 8.8 range. And definitely our good friend phenolphthalein is also a choice. So these two out of that list would be perhaps appropriate to choose. Now, you could really specifically pick a pretty good indicator by just simply doing a theoretical calculation of what your pH should be based on the molarity of your base, based on the molarity and volume of your acid you're starting. You could just do a calculation like we did in that example and go, okay, definitely theoretically at the equivalence point, it should be this number. And you can really dial in really a super appropriate sort of indicator by just simply doing a quick calculation to figure out what that pH should be at the equivalence point. Any questions on how to choose there? Any questions on titrations at all? All right, I can't believe it's happened, but we're done with 14. After 42 weeks of 14, we are done with it. Can't believe a new number, 15. It's like 14, but one more. Here we go. Good news on 15 is it's relatively short of a chapter, so not too much going on, but a lot of stuff going on in terms of complications, but not a lot of sort of information in a sense. So we're here at chapter 15. We're going to talk about KSP and KF because frankly, at this point, we don't have enough K things to talk about here. So KSP is what's known as the solubility product. So I'm just going to go out on a limb here and say that it has something to do with solubility. Yes, so this is the equilibrium constant, as we'll talk about, that has to do with maybe some of those solubility rules that you remember, I'm sure. And then we're going to talk a little later on about KF, which is the formation constant. And the formation constant is actually for typically what are known as complex ions. For example, we've seen a complex ion earlier on in one of our experiments, like this guy right here, a complex ion or something like that. So that's an equilibrium constant that is for complex ions. We could add that to our ever-growing list of K values that we've talked about. So we're going to start with the KSP, which has to do with solubility. And really, even things that are based on solubility rules considered insoluble, which typically means that you would get a solid, right? And you get a precipitate, right? If you put those two things together. So if you look at solubility rules and it says that it's insoluble, that's the stuff that makes a solid. Even things that are technically insoluble has some degree of solubility. So even though the solubility rules say when you put those things together, you will get a solid. And sometimes it's taught like in Chem 50 and earlier that those are for sure always the case. Like, hey, if you throw together silver and chloride, you're always going to get a solid that's going to form. And the truth is not always the case. There are actually a lot of factors that affect whether or not, for example, you will actually see that solid actually form. There are things like common ions, there are things like pH, and there are things like the actual molarity or concentration of your ions play a really big effect in whether or not you'll actually see a precipitate or that solid form. So even though solubility rules tell you that when you put those two things together, you should get a solid, they are under kind of specific conditions of right concentrations and stuff for that solid to actually occur. So because there is a slight degree of solubility in anything, it actually things that are insoluble, right? This is from our solubility rules flashback, right? Chlorides, bromides, and iodides are soluble in everything except for which three things? I'll give you a hint. Silver is one of them. Yeah, so silver. Yes, lead 2. Yes, that's what you were saying there. Yes, and also mercury 1. Yes, so a little silver, lead, and mercury are the exceptions, which means if you have any of those combinations, you will get a solid that's formed based on solubility rules. So because it does set up an equilibrium, we could actually write an equilibrium constant for it, which is known as the KSP. And the KSP is no different than any other equilibrium constant. It is products over reactants. But in this case, obviously, our reactants is a solid, so we do not include it like normal. We don't include solids or liquids in there. And that is typical for KSP expressions because the way KSP reactions are written is usually just like we see here. Usually these guys are written with solids on the reactant side, goes to aqueous ions on the product side. So typically when you write the KSP expression for anything that's typically insoluble, it's just going to be the product side. So that's typically all you're going to have are the ions that are present. That is why we still have silver times chloride here. We could do it for other things as well, magnesium fluoride, a little silver carbonate. We still do what we normally do, which is, in this case, we break apart into 1 magnesium and 2 fluorides. We still need to include that as the exponents, just like we do in a normal equilibrium expression. We have 2 silvers, 1 carbonate, so again, 2 and 1. We have 3 calciums and 2 phosphates, so we would include that. Again, this is typically how all these reactions are written: solid on the left, aqueous ions on the right, and typically these are going to be your only ones that are present. Now, we could also use to help us decide, for example, will we actually get a solid to form? And we could use our friend Q that we saw earlier. Q is still the same thing. Q is the reaction quotient. And if you remember, we used it when we did equilibrium to decide, is the system at equilibrium? And if it's not at equilibrium, which way it needs to go to reach equilibrium. Q is calculated the same as K, basically, right? And the expression is the same. So if you were going to do Q for this guy, Q would be the concentration of silver times the concentration of chloride. And you could compare Q to the KSP value. And if Q is less than the KSP value, you could actually go opposite of where that's pointing. You will go opposite in the equation to the right. And on the right-hand side, we have aqueous ions, which means you would have basically an unsaturated solution at that point, and you will not get actually a precipitate to form. So again, if you threw silver and chloride together where Q is less than KSP, you're not going to see a solid form. So even though it tells you should, because the concentrations are not correct, you will not get really that solid to actually form. If you have Q is equal to the KSP, that basically means you have a saturated solution. And if you remember the definition of a saturated solution, that is a solution where you have hit the maximum amount of solute that will dissolve in that solvent. Basically, you max out as much like solid you could get to dissolve. Pretty much if you put like another crystal or two there, the solid in there is not going to dissolve, and you will get a precipitate. So that's kind of right on the edge of, we're going to drop down to Q is greater than the KSP value. Again, if you go opposite of where that's pointing, with obviously Q on the left there and K on the right, we go to the left in the equation, that is solids, which means you will have a supersaturated solution, which basically means you have way too much solute in that solution or that solvent. It's not going to dissolve, and you will get a precipitate that will form. So we could calculate Q if we have enough information and compare it to the KSP value, and we could actually make a prediction as to whether or not we will see a solid form. So again, this goes back to the idea, as I talked about a second ago, that although solubility rules may say that we get a solid, again, something like concentration plays a really important effect. Any questions on that there? Now, when we talk about KSP as really being the equilibrium constant for things that are insoluble, would you expect the KSP value to be large or small? So if these are for things that are typically solids, right? Which side is my solid typically on in this reaction? It's on the reactant side, right? Which means I probably will have more reactants than products, right? Which means my KSP value most likely are going to be small. Yeah, and they would typically be very, very small values. And that is typically what we see here. If you take a look at this, they are really small values. Some of them, or a good majority of them, like to the minus 39, to the minus 28, minus 11, minus 15, there's some pretty big minus 48, minus 40 something. So typically speaking, when you look at the KSP sort of value, it is a really, really small value. So what that really means is, as we've talked about previously, is, something where you have your solid and it obviously has your ions on this side that's aqueous. This guy's solid. Since we have a really small KSP value, which is an equilibrium value, we should mainly have reactants, which means we should mainly have that precipitate there. But because it's an equilibrium, we will still have a little bit of it, breaking apart into its ions. And here's some more from your book there, some more values. And again, you can see pretty big values, minus 54 on some of them. So they're very, very small. So when we do calculations involving KSP and solubility, there's two types of sort of solubility that we sometimes calculate. One is the molar solubility, and molar means molarity, is essentially the moles per liter. So when you calculate the molarity, that is the molar solubility, which is the number of moles you could get to dissolve in 1 liter of solution. But sometimes we want the solubility in grams per liter. And that also is just the regular old solubility. It tells us basically how many grams you could dissolve in a liter of solution. Now, when we have these problems, there's really two ways that we do these calculations. One way you don't necessarily have to do an ice table, and one way you do need to do an ice table. But you could use an ice table for both ways, which will help you sometimes not mess up the calculation. So sometimes when people kind of don't do the ice table way, they sometimes mess up the calculation. I'll explain to you as we go through it, what sometimes happens. But it really depends on sort of what was given to you in terms of the problem, what you're trying to find. So for example, if you're given the solubility of your compound in whatever units it is, you're trying to find the KSP, you don't necessarily have to do an ice table, but you can. But what you would want to do is take the solubility again in whatever units they give it to you and get it into basically molarity of the compound. And then you want to figure out the molarity of the ions. And from that, you could get to basically the KSP expression by just plugging it in to the KSP expression and get the value. Now, the place where you might want to use an ice table is there, would be a good idea, kind of pretty helpful. But definitely on the second sort of problem that you'll come across, you should use an ice table. And in this problem, basically all you're going to be given is the KSP value. So you basically are just going to be laid up, hey, what is the solubility of this thing? Again, in whatever units they want the solubility to be in, moles per liter, grams per liter, kilograms per milliliter, some weird unit. They're just going to basically ask you, what is the solubility of this substance? And all they will give you is the KSP value. So you will do pretty much an ice table, and that will allow you to figure out the molar solubility of your compound. And from that, obviously, you convert it to whatever units you may be looking for. So again, probably the safer approach is to kind of ice table up both ways, regardless of sort of what's asked of you. But really, in the first way, you don't necessarily have to do it. So let's take a look at an example here together to kind of show you how we work through these problems and a little bit of maybe how it's slightly different to some of the other equilibrium problems that we've done. We're looking for the solubility of silver phosphate, which is Ag, dramatic pause, 3PO4. I'm not sure why the dramatic pause there is in the formula. At 25 degrees, and the KSP there is, or the solubility is 1.6 times 10 to minus 5. We're actually looking for what the KSP is here. So if we were going to do this, we technically wouldn't necessarily need to do an ice table per se, but I'm going to do an ice table to show you how it will probably be beneficial for you to do it. So the first thing that we're going to do is we're going to take our guy. And by the way, we know that this is a solid because, frankly, we're looking for a KSP value. So this is where if you're not sure on your solubility rules, you could pretty much fake it because as there's the KSP value, that's going to be a solids, right? So that's all you have to worry about. And here, it's going to break apart into 3 silver ions and a phosphate ion. Yeah. That means that I can write my KSP expression in this case, which would be the concentration of silver, and I do need a qubit because of the coefficient. And that's going to be times the concentration of phosphate in this case, right? And that's going to equal pretty much what we're looking for in this particular problem. All right, so we're going to go under the assumption that we want to do an ice table here, and I'm going to show you how the sort of the ice table looks so that when you definitely need to do an ice table, you know how to do it. So initially here, we usually do not worry about things that are solid, right? Because they're not in the equilibrium expression. And that means when I get to my ice table here, I'm not going to worry about at all the reactant because it's a solid, right? So I don't have to worry about it. Normally, if we're not given any numbers per se, we normally will start out with 0 of these guys. So now we normally will come to our change part here, and we will have minuses on the left and positives on the right, and we will still have that here. We do actually a lot of times use a different symbol or letter to represent the change. Normally we use X, but here we sometimes will most of the time use S. And S actually stands for the molar solubility. That is, again, a fancy way of saying molarity. It's basically what it stands for. We're still going to do the same thing, which means we do need to take into account the coefficients, right? So this should be plus 3x, and this should be plus x because of the coefficients. Just, I used x even though I just said s. I want to put s in there, so I'll actually use the right one. But that would be like we would normally do it. Yeah, that's what I was trying to do. And this would be 3s and s at this point. Yeah. At equilibrium here, we end up with 3s and s. Any questions on that ice table there? So normally at this point, right, if we had the KSP, we would throw that into our KSP expression, and that would give us basically that KSP would equal 3s, and it needs to be cubed, times s. And normally if we had a KSP value at this point, we could solve for s, right? We could actually solve for the molar solubility, and then we could figure out, the solubility of it. In this particular case, they actually gave us the molar solubility, which is this guy right here. That's in molarity. So really that number equals S, 1.6 times 10 to the minus 5 molar, which means at this point, that is that S and that is that S, which means my KSP value in this case should be 3 times 1.6 times 10 to the minus 5 cubed. times 1.6 times 10 to the minus 5. That's going to give me a KSP value here of 1.8 times 10 to the minus 18. So a large or small value of K? Is a small value of K, right? Which we would expect since this is pretty much insoluble, and we would expect to mainly have reactants there at equilibrium. Question on that. So earlier I said that you really don't need to do an ice table, and you don't necessarily have to do an ice table, even though you might need to do, whoops, wrong way. There you go. This way. What you could do is, again, if you understand concentration, just come here. You could have just find a place to write, I suppose. Get rid of that big arrow. Maybe let me get rid of that. All right, we'll go here. So if you understood concentration and how it works, you could have just took the equation like we had there and break it up into silver and phosphate. And because the concentration of this was 1.6 times 10 to the minus 5, you would know that you need to take 3 times 1.6 times 10 to the minus 5. And because this is a 1-to-1 relationship between those guys, this guy would be 1.6 times 10 to the minus 5. And you could just take those guys and pop them right into the KSP expression without, doing the entire ice table and stuff like that. So you could definitely, if you understand how the concentrations break apart into the concentration of the ions, you could just put those concentration of the ions, the correct ones, into the KSP expression, and you would get your answer. The reason I would recommend doing the ice table approach, even in this case, that you could do that, is people oftentimes question themselves of, I multiplied by 3, do I still need to do that 3 as well? And they oftentimes will do just one of the 3s, like oftentimes the cubing part without multiplying it by 3. So it's a very common mistake that people make, is that part of it. They either think like, I did it once, I don't really need to do it twice. So the benefit of sort of doing the ice table is it tells you you need to do it twice, basically, when you're all said and done. And then you should hopefully get the right answer at that point. So that's, again, a very common mistake that sometimes people make, and the ice table could help you sort of visually see, oh yeah, I gotta go 3s and also cube it, so I need to multiply it and also cube it rather than just cubing it, which sometimes people miss, like this part of it. They just go, oh cool, that's the concentration, I'll just slap it in here, and they get the wrong answer or stuff like that. Any questions on that there? All right, I did one, you do one. What is the solubility of silver chloride? The KSP of silver chloride will go with 1.6 times 10 to the minus 10. And we want it in grams per liter. So, molar match the silver. 107.9, I think. It's like an eye test to see how I did. And chlorine should be 35.45. I think it's pretty close, 107.9, maybe. Okay. All right, so calculate it up. What is the grams per liter solubility of silver chloride? So in this case, the only thing given to you is the KSP, which obviously, if it is not given to you, you might need to look up in a table in the book. So this is definitely a situation where you should definitely do an ice table. So we're going to start with silver chloride, which is our AgCl, and it is a solid. By the way, again, I know it's a solid because it has a KSP value, so that's a big hint. It's going to break apart into a silver ion and a chloride ion. And we can write our KSP expression here. I'll go over here, maybe. KSP will equal, again, our silver times our chloride. Again, our reactants is a solid, so obviously not included like typical in these problems. Times 10 to the minus 10, 1.6 times 10 to the minus 10. We're going to do an ice table here. So not worrying about the solid. Initially, we're going to have 0 of these guys as nothing was given to us. Change here is going to be plus S and plus S. And that means at equilibrium, we will have S and S. Any questions on the ice table here? Like a normal equilibrium problem, we're going to slap these guys basically into here. And that's going to get us basically S times S, or S squared, is equal to 1.6 times 10 to the minus 10. That's basically S squared. We're going to square root both sides, and that's going to give us an S value here after we square root that guy. What did I get there? 0.0000 zeros. 12649. Yeah. First off, any questions on that there? That is the molar solubility, right? That is the molarity. That is the concentration, by the way, right? Of the silver ions at equilibrium is basically this number there. Whatever number I got there, 0.00001264.9. That's also the chloride's concentration. And since we're interested in silver chloride, that would actually be the silver chloride's concentration as well, because it's a 1-to-1 relationship going backwards. Also a 1-to-1 relationship going backwards. So this is also, I don't want to write the number again. This is also the silver chloride's concentration as well. So typically in these problems, when you actually do solve for S in a table like this, it is actually the solubility of the whole thing together, basically, is what it is. In this case, it's the solubility of the ions as well, because each of the ions is only equal to S. But if I had one of the ions that was equal to 2S, I would need to multiply that number by 2 to get that guy's concentration. So it's not always necessary the concentration of each of the ions. It is if it's a 1-to-1 ion, but it is the concentration of the whole thing together. So what that means is that is my concentration of silver chloride in this solution. And that means that we got 0.00001264.9. We have basically 1.2649 times 10 to the minus 5 moles per liter of silver chloride. I am interested in the solubility in grams per liter. So if I have moles per liter and want to end up in grams per liter, what is the thing I need to do that conversion? That is the molar mass from the periodic table, which are grams per mole. Yeah. So you need the molar mass from the periodic table to do that conversion. So if you add up the molar mass from the periodic table there, that's 107.9 plus 3545. That is 143.4 grams per mole silver chloride. Moles cancel. Gonna give us here our solubility of our silver chloride as being 0.0018 grams per liter. Is that a big solubility? That is not. That basically means that you could take, in these conditions, under normal conditions, basically 0.002 grams of silver chloride, and you could get that to dissolve in 1,000 milliliters of water. That is like a super low solubility, right? It is not very soluble at all. And that is why when we look at something like silver chloride, we usually think of it under normal conditions as it's going to be a solid, right? It's going to precipitate out, because under normal conditions of 25 degrees, pretty much, you can only get about 0.002 grams to dissolve in 1,000 milliliters of water. And that's not a lot. Yeah. Any questions on that calculation there? All right, we're laid up there for